Okay, let's get started. So are there any questions from last lecture or any questions at all? When does your first assignment go out? On the 24th. Well, what day is that? This Friday, okay? So just so you're aware of when things go out and whatnot. When do office hours start? Which week? Next week or this week? This week. So if you have any issues setting up your environment, please come to my office hours, come to any of the 3 TAs' office hours. One of the TAs has office hours today, I think one on Tuesday, then me on Wednesday. There are 4 days that you can go for office hours. There's 1 day missing, I forget which. So are there any questions at all, though? Yeah.
Just to clarify, labs start next week?
Right. Labs start next week. There are no labs this week. So don't go to the lab section. The TAs will not be there. I mean, you could go there, but it's just, it's not going to be helpful for you. Any other questions? Okay, so what were we talking about last time? We were talking about quite a few things. So we wanted to program it all. So why should we care about programming? Well, we noted that to have a program run on a computer, we need a person to actually code up the program and then make it run. And then we noted, well, to actually do that type of thing, we need to understand, well, there's the technical aspect of actually writing the program in that language, but also there's an art to it in the sense that you want to be able to have the program behave nicely with the user or other programs, that sort of thing. But to actually understand how to actually program something for a computer, we need to understand how the computer actually works. And one aspect of that is the hardware of the computer, mainly the main components that we saw, the CPU, RAM, and we haven't gotten to the other 3 yet. So we saw that the CPU was composed of mainly 2 units, namely the control and the arithmetic logic units. So these 2 are, so other processors do have other things in them, but pretty much every processor has these 2 things built into them. So one of them handles when it sees an instruction, what does it do with it? And then one of the units handles, well, if you're doing a computation type of instruction, like adding or subtracting, that sort of thing, it's fed off to the ALU to do the instruction there. But other instructions, they do other things. But how does the CPU actually work? Well, the 3 main cycles that we saw, the fetch part of the cycle, which is you get an instruction from main memory, although that's not technically true, but it's a good model to think how it actually works. Then we have to figure out, what is this instruction actually supposed to do? What do we want to do in this situation? That's the decode step. And then the execute is just run the instruction, do what the control unit says to do, or the ALU says to do, and then carry on by going back to the fetch, decode, execute step, and then just keep going over and over and over. And then, so that's the CPU. Main memory is where we hold all of the programs that are actually running. So they initially are on our hard drive or solid state drive or whatever. And then when we run them, the program's brought into main memory where it is actually executed. The main reason why we want to do this is that RAM is much faster than executing off a disk, but has a disadvantage in that it's volatile, meaning that if you turn the computer off, then main memory is wiped. But the cool thing about RAM is that you can access any address, any place in memory, and it'll take the same amount of time, relatively. Okay, so how is, and then we got to this slide at the very end of last time. So how is it, what things are in main memory? Well, we saw that a bit is a 0 or 1, and a byte is just 8 consecutive bits. So 8 bits for 1 byte. And main memory is composed of many billions, or even trillions in some cases, bytes. And so is your hard drive. So if we want to understand what binary numbers are, we need to be able to understand, well, how does our program, like we write it in English, but it needs to be converted into binary somehow, how does it actually do that? So everything is stored in binary, as you might expect. So I can go deep into the rabbit hole about this, but pretty much anything that we're going to deal with in this class is what is called ASCII text, which is stored as a number between 0 and 127. So how many values are between 0 and 127 inclusive? 128. So is there anything special about 128? 2 is a power of 2, right. So if you think about it, if you have n bits of memory, so let's say 7, for instance, well, how many possible things could I address or represent in those n bits? Well, I have 2 choices for the first bit, 0 or 1. What about the second bit? Is it independent of the first bit, whatever I set the second bit to? So does the second bit, whatever 0 or 1, does that depend on what the first bit is, if I want to address something else?
Yes.
You sure? If I set the first one to 1, then the second one has to be set to a 1? No. So I have 2 independent choices for the second bit. What about the third bit? Same thing, same thing, same thing. So I have 2 choices for the first bit, 2 choices for the second bit, times 2, times 2, times 2, times 2, and I have n of them. So therefore, I have 2 to the n possible things that I can address with n bits, or represent that sort of thing. So, and that'll be important when we get to integer representations and whatnot. So, but in order to actually to understand how the program actually is converted to binary, we need to understand, well, since all our text that we're going to be using is represented as an integer between 0 and 127, namely, well, how do we convert any number, for example, into binary? So the way you do this, and we'll do an example of this, is you find the highest power of 2 less than or equal to your number, your target number, and then you write a 1 in that case. Then what you do is you keep dividing that power of 2 by 2. So if it was 64 before, now it's 32, and then you do the check again against the original number minus the power of 2 you started with. And then you keep going until you reach 1. If you can't subtract that number off the number you currently have, then you write a 0. So if you can subtract, you write a 1. If you can't subtract, you write a 0. So how do we actually do this? Let's do an example. So I have this example right here. Convert 74 to binary. So what is the highest power of 2 less than or equal to 74? 64, right. So I'll write current power of 2 is 64. So if I take 64 away from 74, can I subtract 64 from 74? Yeah, and still have a positive number, namely. Yeah, I can. So what is the resulting number after I subtract 64 from 74? 10. So I'll keep resulting number is 10. And then because I could subtract 64 away from that number, I write a 1. So I'll put resulting, learn to spell, resulting binary number is currently 1 so far. And I keep that 1 there. Now the resulting number is currently 10. And I take 64 and I divide it by 2 to get 32. So 32 is now the current power of 2 I'm working with. Can I subtract 32 from 10 and still have a positive number? No, I would get a negative number. So I write a 0. Because I can't subtract that power of 2 away. Now, then I keep dividing by 2. So I get 16. Can I subtract 16 from 10? No. So again, I write a 0. Now I divide again. Should make this a little bigger. So I have 8 now. Can I subtract 8 from 10? Yes. So remember, this is not 1, 0. This is 10. So I can subtract it. So I'll get a 2. after that. And then I write a 1 because of that. Then I divide the current power of 2 by 2 again, so I have 4. Can I subtract 4 from 2? No, I can't. So then I write a 0. Then I divide by 2 again. Can I subtract 2 from 2? Yes. And still have a, I should say, non-negative integer. So I can have 0 in this case. So then I can subtract it, which I'll get 0. Then I write a 1, because I can subtract it. Then I divide by 2 again, and I get 1. Can I subtract 1 from 0? No. And so then I write a 0. Are there any powers of 2 that are integers less than 1? No. So 1 is the last step you need to do. So this is the resulting binary number for 74. Well, how can you verify that this is correct? Well, let's see. What is the last, so this is called the least significant bit, the one on the right. So that is a 0. What does that correspond to in terms of the power of 2? Is it the 1's place, 2's place, 4's place, 8's place? What is it? The 1's place. So this says have 1 times 0 plus 2. Well, the next place is the 2's place. Do I have a 1 there? Yeah, so times 1 plus, well, the next power of 2 is 4, but I have a 0 there. So I have 4 times 0. Next one is 8, and I have a 1 there. Plus 16 times 0, plus 32 times 0, plus 64 times 1. Good. And then if I type this into Spotlight, I do, although it's in small, I guess here it is. So it is 74, and then we have verified that this is the power of 2. So in this idea, you can actually convert any positive number into binary by just saying, well, what is the highest power of 2 less than this number? And then just keep dividing that number by 2, and then keep trying to subtract it off the resulting number you have. And if you ever, once you reach 0, or the power of 2 reaches 1, then you're done. And then you can verify it by just doing an addition and multiplication like this, by just looking at the powers of 2 you have and multiply it by 0 or 1 accordingly. Any questions on how to convert to binary? Yeah.
So the number at the end that is simplified down to will usually be 1. So like 432, 16,
It always has to be a 1, because you keep dividing by 2 starting with the power of 2. So that means eventually you'll reach 1, and you can't go any further because there are no integers that are powers of 2 less than 1.
So the pattern will be the same?
In terms, well, the pattern here, you start with the power of 2 and you divide by it, but the resulting number is going to be dependent on the original number. Yeah, because the original number, of course, might not be a power of 2. If it is, then it's just going to be a 1 followed by a bunch of zeros. But here, you don't know necessarily where the 1s are going to fall. Yeah, way in the back. Well, why the number 2? Because we keep trying to subtract 64, then 32, then 16 away from 10, and we couldn't do it while maintaining a positive number or a non-negative number. So I can't subtract 16 from 10 and get something that's 0 or greater. So then I keep trying. Well, I get down to 8, then I can. So then I write the zeros for the 32 and the 16 place. Then once I get to the 8th place, then I write a 1 because I can subtract it away.
So the computer basically understands that 1001010 like a code to 74.
Yeah. Well, the computer doesn't really know anything. It just sees zeros and ones. But if we wanted to print that as a decimal in base 10, then it will print 74 for sure. So like if we remember from our program here, we had like 212 and 5. When this is compiled to a binary, it's not actually storing 212 there. It's storing the binary number. So then when we want to print it down here, it'll actually do the the conversion back to base 10 and print that number for us. But the computer doesn't say, oh, this is 212 or this is 74. It just sees zeros and ones. Okay? Any other questions? Yeah.
How many digits are you supposed to get for binary?
So when we convert this, so it. So I'll give you the technical answer, but you're not required to know this. It's the ceiling of log base 2 of the original number n. So if you think about it, well, we're dividing by 2 every single time. So you have to think, well, what is the power of 2 such that 2 to this number is at least n, or at most n? So then you just say, well, you're dividing by 2. Well, that's just essentially just the log. The logarithmic number of times you're dividing by 2 to get down to that number. But you're not needed. You don't have to know that. But it's because you asked the question. Other questions? Yeah.
How would the computers store non-numerical data?
You mean non-integer data? That's a whole rabbit hole in itself. So that's called floating point, and we'll get to that eventually. But the way it does it is every number, whether it's a real number or not, a real number or an integer or whatever, can be of the form some number times 2 to some power. So think of scientific notation. Something times 10 to some power. Can you represent any number that way? Any positive number that way? Something times 10 to some number? Yeah, you can do that. Same thing with binary. And the way it does it is it stores that number at the front and the power of 2 in an efficient kind of way. Other questions? Yeah.
What if it's just like, very before we try to convert 108, and we use 100 as like the nearest square?
No, I said you have to start with the highest power of 2 less than or equal to that number. So in the 108, right? So what's the highest power of 2 less than or equal to 108? 64. So you'd have to start with 64 again. So then in that case, well, for 108, well, if we try 64, we can subtract it. Then if we looked at the resulting number, we have 34 left. So what's the next power of 2 below 64? 32. Can I subtract 32 from 34? Yeah, so then I'll write a 1 again. 16, then the resulting number after that is 2. So I can't subtract 16, 8, or 4. But then I can do 2, which I write a 1. And then the resulting number is 0, so then I have to write a 0 at the end. So you start with the highest power of 2 less than or equal to that number. What if I started with 64, which is a power of 2? Can I subtract 64 from 64? Yeah, so it would be a 1, but then the resulting number is 0. So what's the rest of the number? Zeros. Right, good. Any other questions? What if I wanted to do base 3? I would have to look at powers of 3 and divide by 3. Good. So we actually do this with decimal. You just take the highest power of 10 less than or equal to that number and divide by 10 every time. It's the exact same thing. Other questions, though, before we continue? Yeah. What's that? No. If I had 129, then it'd be 8 digits. So that's why I said it's this number. So if you have 128, well, log base 2 of 128 is 7. And then the ceiling of 7 is 7. So if you have 129, well, that's going to round up to 8. Other questions?
You use you can only use positive integers, not negative, to find the.
Right. Yeah, because you can't represent a negative number in terms of powers of 2. Yeah, so that's the problem. Yeah. Great question. So what we're going to do is we're going to talk about something that's called unsigned and signed integers. So I'll give you the spoiler. So in the integer representation for a signed integer where it can be negative, we put what is called a sign bit in the number by saying if it's 0, that sign bit, then the number is positive. If it's 1, then the number is negative. So we handle it that way. Other questions? Great questions. All right, so we got that. Hopefully we know how to convert any positive or, I guess, non-negative integer into binary. Cool, so we are now done talking about RAM. So the next one on our list was secondary storage, namely the hard drive. And we're just gonna speed through these because it's not really that important, but it's just, instead of volatile data for RAM, it's for us to store whatever files or programs we want onto our drive for long-term storage. So if we turn the computer off, then the files will stay exactly where they are, unless the hard drive breaks. But assuming the hard drive doesn't break, then they'll stay there. So there are some forms of secondary storage. The one that we use most often is a hard disk, or I hope you're using a solid-state disk because obviously those are faster. But they're stored magnetically, although that's becoming a little less common nowadays. But of course, you can use a CD or DVD if you're really old or something, if you want to burn your music collection onto a CD. Does anyone do that anymore? One person. Props to you. But it's definitely becoming less common than it used to be. So like in the early 2000s, even Apple was selling like whole stacks of CDs and DVDs to burn their iTunes music collection onto them. But it's definitely not true anymore. Was there? yeah, Napster and LimeWire, yeah. But of course we can use a USB flash drive, which I do sometimes as well. Okay, so it's just an understanding of we have secondary storage available to us. And then, of course, if we want to actually put something into our program from somewhere else, maybe from the user or from the internet, we need an input device. So there are many ways you can do this. So this is part of the artistry part in programming, where if you need some data from the user, you have to think, well, how should I make this easiest for the user to provide me the necessary data? So if you need like an image or something, well, you could ask the user to take a photo on their phone or print it out or whatever and then put it into the computer in some other way, or you can maybe use the webcam. You have to think about, like, if you're designing a particular application, what types of input devices will you use? So the one that we're going to use pretty much the entire class is the keyboard, or maybe from a file or something. But the main one is from a keyboard. But you can see how you can use other things like the mouse or the microphone, all that stuff. But once we do that, we need to tell the user results once you run that program, right? So we need an output device. So the main one that we're going to use is a computer screen, right? So remember when we ran that program, we printed out the result was 217 from the calculation. So that's the main interface that we're going to use in this class. But in some other classes, as you go through your program, you may want to think of other ways you can output to the user. Maybe you show an image, or you send something to another server. So many ways you can think about doing this. Any questions on these last three things? The secondary storage, input, and output devices? Okay, so we talked about the hardware aspect of a computer. What's the other aspect of a computer, mainly? The software part. So we need to think about, well, there's clearly stuff running on our computer already. Well, we need to be able to think, well, how are we going to interface with that if we need to? Or if the computer does something with its software, do we need to handle anything with our software that we're going to write? So if we understand how systems on a computer operate and what they are actually, then we can actually get some insight on how to make our own programs. So the main one that we're not going to actually do in this class, but just to be aware that these exist, something called system software. So things that already exist on the system that are not written by third-party developers or yourself. Something that's provided by the manufacturer or by Apple or Dell or Windows or something like that. So, of course, the most important one is the operating system. So this is, as you might expect, it controls the operation of the computer. So from the startup of the machine to the visual interface to how does it handle file storage, how does it handle network security, all that type of stuff is handled by the operating system. So most of you, as I can see from here, are using Mac computers. Some of you are using Windows computers. Anyone running Linux?
Yeah.
One person again. So again, props to you. So of course there are other operating systems that you can use, but of course the three biggest ones are Windows, Mac, and Linux. If you want to connect something to the computer, the operating system loads the drivers so that you can actually now interface with that particular device. So if I stick something into I have a MacBook Pro, it'll show on the side panel, oh, you have connected this device, and if I click on it, I can access the files within that drive that I connect in any way that I would access any other file on my computer. So the operating system handles how do you connect with other devices as well. And it allows programs to run. So if I wanted to run some program that I write, I ask the operating system, run this program for me, and then it'll fetch that program, move it to main memory, which is needed for it to run, and then it'll ask, okay, CPU, run this program that's at this address in main memory. And then it'll do the fetch, decode, execute cycle that we talked about. But there are other programs, not just the operating system, called utility programs. And these ones are not nearly as common, say, as the operating system, but they help enhance the computer operations. So the main one here is for the visual interface. So the operating system is only responsible for the low-level stuff. How does it connect to various devices? How does it handle security? But one of them is the visual interface, is a utility program that helps enhance that sort of thing. But other ones that you may want to consider are file compression or virus scanners. So if you want to compress some files to a zip format or 7-zip or something like that, that is a utility program that is working with the operating system but is not part of the operating system. But another one like data backup. But we're not going to write programs like these. We're going to write something that's called application software. So these ones that directly provide services to the user. So what's an example of an application software? What's that? Google Chrome or any web browser. Yeah, other ones? Yeah. PowerPoint or Word or Excel. So things that are written by third-party developers that work on top of the operating system. So they're not operating system part of it, or utility programs, they run on top of that. And the way that they work is that the operating system provides an interface for those programs to say, oh, here's how you save a file. You call this function. So the application software says, like, when you want to save, it calls that function and it forwards whatever it needs to the operating system that handles all that stuff for you. So if you want to save a program, say in C++, you don't write all of the utilities to say, write this bit here, write this bit here. You say, you forward it to the operating system via a function call by saying, I have this string I want to write to the secondary storage. Then I call this function with that, and then the operating system handles it for me. So application software is built on top of the operating system, and they provide services to the user, as you might expect. Any questions on these two? Okay. And then, of course, you can have games, that sort of thing. Those are all application software.
And just to clarify,
Yeah.
if we miss any section of the content, we can go on Blackboard and see see a video on this one?
Yeah, remember that there's a playlist link on the course page.
Okay.
Yeah, so make sure to bookmark the course page because all of the things that are not related to grades or actual submissions of things will be on the course page. So the first video is already up, and a lot of you have already watched it, which is good. But once I do this one, I'll upload that and then ad infinitum until the course ends. Yeah, so they're also on the course page. Yep. Any questions about these, though? Well, one thing I actually kind of recommend is don't take notes in class because it allows you to focus more instead of focusing on writing. And if there's something that you didn't quite get, write that particular topic down and then watch the video or look at the PowerPoint later because it allows you to be more focused on what I'm actually saying versus writing every single thing down because all of this is provided to you anyway. But any questions about systems? And if I'm going too fast, please tell me to slow down because I like talking fast and people don't. So tell me to slow down if I need to. Okay, so those are the hardware and the software of the computer. Now we need to understand, well, how do we actually even program for this computer? Well, one of the important things about programming in general is understanding what types of things you're going to solve. So, for example, if you're going to be writing something low level, like a faster file compression format or something, or are you writing something high level, like a game or an application for that matter? So you have to understand which type of thing are you going to actually try to build. And then from that, you need to say, well, based on which of these I'm going to do, what programming language is going to be best for me? Because as you might expect, there are gazillions of languages, programming languages out there, and some of them are better at some tasks than others at other tasks. So you have to think, well, what are the strengths and weaknesses of the language we're going to be working with? Fortunately, I've decided the language for you, which is C++, so you don't have to make that decision. But when you're doing this in the real world, you need to actually think about this sort of thing. So a program just in general, as we kind of already saw, was just a bunch of instructions that do something. So nothing special there. So a programming language is just a language that people write to write programs. So C++ is a programming language. So, or Java is a programming language. Python is a programming language. There are many such languages. And then there are two types mainly. So the two types are not necessarily black and white, like one is low level and one is high level. Sometimes they're a mix of both. And in the case of C++, I would actually say that it's a mix of both. But one of them is for low level, as I kind of already said, which is where you access the hardware directly. So the reason why I wrote that this is not very easy to read is that you need to sometimes write this low-level code that is closer for a computer to understand and not necessarily easier for a human to understand. We understand English and many other spoken languages, but we don't understand, well, if I have this string of zeros and ones, what is the computer going to do? We don't understand that. So that's less common today than it used to be because for a high-level program, which is closer to human language, we have much faster computers that allow us to be able to convert it over to this low-level format for us. And so instead of us actually writing the low-level code, well, we write the high-level code that'll be transformed into the low-level anyway. But sometimes the high-level code is too hard for what's called a compiler to understand to get a very fast program in low-level code. Anyone used to play Roller Coaster Tycoon? I actually still do. So if any of you have Android or iPhone or something like that, you can actually play Roller Coaster Tycoon Classic right now. And so I've been playing that for the past few years. But anyone know any cool facts about the original Roller Coaster Tycoon? Yeah. Right. So it was written all in this low-level language called assembly. What's amazing is that it took roughly 3 million lines of handwritten code to get this amazing game, to eke out every single clock cycle of your computer as fast as it possibly can run. Because way back then, the processors were moderately fast, but the amount of RAM that you can use was very small. So on the order of kilobytes in size instead of gigabytes that we have now. So back then, it was much more important to handle how do you do this in a low-level environment and understand this assembly language. Fortunately, we're not going to touch that in this class. We're going to stick to the high-level part of it. Any questions on programming languages? Yeah. I have no idea. I would search that. For something that large, I would say that so there's a thing in programming languages called don't reinvent the wheel. So what you do there is you have this giant library of code that may involve many different languages, and maybe this other library, and you try to bridge them together with your own code, depending on what type of language you want to use. So if you want to eke out every single clock cycle, say in a game like that, you would probably write it in C++. Because it's high level enough that people can actually write it, but it's fast enough that it's essentially you just wrote the low level version of it. So probably C++, I have no idea. Minecraft is written in Java, so as an example. And so Java is a pretty fast language and it's high level as well. But C++ is even faster than Java. Yeah. Yes, Unreal Engine is written in C++. Largely, yeah. So of course it depends on the operating system, because if you want to access graphics hardware, there are special languages for those that are not C++, and so you need to interface with those directly, and it depends on the GPU that you're using. Yeah.
Nowadays, like most of the computers, they kind of don't use RAM that much anymore. They use the GPU.
Yep.
So would there be any programming languages that deal more with GPU rather than?
Yeah, so there's one called CUDA, C-U-D-A, that you can access the graphics hardware directly, and that's only for NVIDIA GPUs, but it really depends on what GPU that you're using. But I'm not very familiar with graphics hardware because I don't do that directly.
Why are there so many different languages?
Good question. Because so there's this. Anyone know what XKCD is? So it's this geeky comic where. So there was this one comic where they have, we have 13 standards for this particular application that we're doing. And what we want to do is we want to unify all 13 standards to have a one standard that is best for everyone. What do you think happens at the end? There are 14 standards. So that's actually kind of going back to your question, which is, there are what are called general purpose programming languages. C++ is one of them, but there are specialized ones that are good for scientific computation or graphics work or things like that. So you have specialized languages for special tasks, and then you have general purpose ones. So that's why C++ is one of the languages that is taught in an intro class like this one, because it's a general purpose language. But that's why there are so many different languages. And then there are some esoteric ones, but yeah, I won't go into those. Yeah.
How does a programming language come about? How do you create a new language?
Right. So you think of a problem that you want to solve that other languages don't already solve for you, or maybe they do solve, but are very inefficient at in terms of either the amount of time it takes or how much work it takes you to do it. So then you try to write the language based off of that. So there's a class called CSE100 here, where it goes over, well, how do you actually make a compiler? And then you make a toy compiler for a toy language, and then you kind of say, well, this could be generalized to a bigger language and bigger compiler. Other questions? That's like the best questions of any class I've ever taught, so that's cool. Well, how do you actually run this thing? So we built this high-level language, high-level programming language, and we wrote a program in it. How do we actually run it? Well, we type the program into a text editor. They really do type like this, right? So there are two main things to keep in mind. So the source code is the set of statements in the program, and then the file that it's written in is called the source file. So there are source files, and within source files, they have source code. So it's just a term for the code and the file. So this is unique to C++, but it kind of generalizes, but it's really unique to C++. You run something called a preprocessor. So what that does is, remember the include IO stream? So if we go back to here, remember this include IO stream thing? So what if I just said, well, I'm going to delete that line and try to run the program? What do you think is going to happen?
Error.
Yeah, some error is going to happen, right? So it says, well, it doesn't know what this std thing is, and it doesn't know what cout is, right? So that's actually needed. So this I like to say hashtag include, but it's really # include. So what that is a preprocessor statement. So IO stream it corresponds to another file. So it corresponds to another file, and it says, well, anything that you use in IO stream, the preprocessor is going to say, oh, the cout code that's in IO stream, I'm going to move it to your program. I'm going to copy and paste it directly into your program, and so that it's all in one place. So all that does is just it moves any directives, which is the IO stream thing. It takes any code that's relevant there and puts it into your program. So what we have right now, so you don't actually see that happen, but we still only have a C++ program. It's still just a bunch of programming statements that you and I could read. What happens next is a compiler steps in and looks at the resulting program and then converts it into a form that the computer can understand pretty much. So it converts that source code that you wrote, and then with anything with a preprocessor, into machine instructions, which is called machine code. So it's stored in an object file. And then after that, you run what's called a linker, which links anything that's relevant to the hardware, like the cout stuff, directly to the hardware directly, and then after that, it produces an executable that you can run yourself. So this is how that works. So if we run this program, we just see the end result that corresponds to the program actually running. Well, if we go back and look at, say, the Messages tab, it says, well, it looks at the dependencies. So the target's called 820, based on the day that I wrote. But it looks at, do I need anything else other than what's in the program here? So that, what program does that? Looks for the dependencies. Oops. Which one is it? The preprocessor, right. So the preprocessor looks for any dependencies that are needed. Then it says, well, this building step, what do you think is doing the building step? The compiler part. And then the linking is part of the linker. And then, so we built this target, it says the build finished, and then we call run. So it runs that executable, and then it shows us the result. So anyone using terminal? So 2 people, good, from 1 to 2. All right. So I wrote that same program in this file. I called it CSE100 _820. And then here's the terminal. So I'm in the same directory, and I'm gonna verify that this file really is in this directory by calling ls. So this lists all of the files in this directory, and I can see, yeah, it is there. So if I want to compile this file and do the pre-processing in one step, I call the compiler for C++. Now, I shouldn't say the compiler because there are multiple compilers, but one of them is called G++. That's one compiler. And then I say, well, I'm going to compile this file. And I push enter, and then nothing happens. So what do you think happened? Well, it compiled the file, and it found all the dependencies it needed. What do you think happened as a result? It made an object file. So if I do the ls again to see the files, I see this thing called a.out. So by default, if you don't change it, when you compile a file, it'll produce a machine executable called a.out. You can change this if you want, and I can show you how to do that. But if I want to run a.out, I say a.out. Oops, I gotta do this period slash corresponds to I want to execute this file, execute some file, and I say a.out, and then it prints the result. Okay? Well, if I wanted to, for example, if I want to actually produce a machine executable directly and name it whatever I want, I pass in the -o flag and say, I want to name the object file that comes out. So let's say I want to call it 820.0. So we usually use .o for a object file extension, but we can call it whatever we want. So if I call 820.0, and then I get the same result. Okay, so this is what happens in the background when I'm running in C-line. It's doing the compilation via some compiler like G++, and then it produces an executable, something .o or a.out, and then it runs that executable. Any questions on how that works? Yeah.
So when you do it in C-line, I'm assuming it doesn't show up in your file directory. Does it just delete the out file afterwards?
Good question. I don't know. So let's go to where that file is. Okay, so it does something much more complicated called cmakelist. I won't go into anything about how that works, but it's essentially doing the same thing. But it's not exactly the same.
So if you did that multiple times in C-line, does it make the same?
Yeah, it does the same thing over and over. It actually detects if the program has changed since the last time. And if the file has changed, then it'll do a recompilation. But if it hasn't changed, it'll just run the same executable. And that's really cool if you have a lot of files and you only change a few. It doesn't recompile all of the other files because they didn't change. Hold on, I still got a minute and a half. Other questions, though?
So basically what you did, you took one file and ran it through another file? In Lincoln's term?
I didn't run it through a file. I run it through an executable called G++. Yeah. So it says G++, look at this file, which happens to be an executable, and run the instructions within that executable. Yeah, I still got until 9:25. And other questions? Okay, so just as an overview today is we have this overview of what happens. So you have this CPP file, C++ file. You run it through a preprocessor, and then there's some source code changes depending on whatever is needed. It passes through a compilation step. It makes this .o or .obj or whatever file you call it, run the linker, which is running the actual file, the // thing, and then it runs the program that way. Any questions before we break for today? No, you don't see the changes, but it keeps in memory, well, this is the real code that you should compile. Cool. I'll see you on Wednesday.